Hello students, this is Dr. A.S. Syed. Today we will discuss how to derive the steepness matrix for particular structure. I will explain steepness matrix formulation with the help of three simple numerical examples, two examples of beam and one example of frame to understand how to derive steepness matrix. So let's start. This question is derive steepness matrix of the beam as shown in figure. Take EI constant. If you look at the beam carefully, first to derive the stiffness matrix of a given beam, we have to identify degree of kinematic indeterminacy of the given beam. So degree of kinematic indeterminacy, all of you know already in previous lectures I have explained. At fixed support, dki equal to 0 because there is no translation, no rotation. At roller support, dki is equal to 1 and that is rotation. So at this point, there will be rotation at point B unknown, theta B. Similarly, at roller support at C, unknown is theta C. So dki of this given beam is 2, that is theta B and theta C. Now we know that steepness means what? Steepness is force required to give the unit displacement. That is steepness. So in short, if you want to derive the steepness coefficient of particular structure, you have to give the unit displacement to that structure. Which displacement is unity? The displacement which is unknown. Now in this beam problem, theta B and theta C are unknown. So if you give unit rotation at point B and unit rotation at point C one by one, you will get the steepness matrix. Size of steepness matrix is always square. It is a square matrix and order of the square matrix is always equal to total kinematic unknowns. Indeterminacy, degree of kinematic indeterminacy. So since in this problem kinematic indeterminacy is 2, size of steepness matrix will be 2 by 2. Now since there are two kinematic unknowns, there will be 4 steepness coefficients. If kinematic unknowns are 2, steepness coefficients will be 4. If kinematic unknowns are 3, steepness coefficients will be 9. Right? It is a square matrix. So 2 by 2. So there are 4 steepness coefficients. If you write down K11 and K21, it is the first column, and K12, K22, it is second column. So this we have to determine. Now understand first column of steepness matrix you will always get when you give the unit displacement at the first kinematic unknown. Let assume if our theta B is the first kinematic unknown and theta C is the second. First column you will get when you give the unit rotation at point B, that is theta B equal to 1. And second column you will get from when you give the unit rotation at point C, that is theta C equal to 1. Okay, so now we have to give the unit rotation at B and unit rotation at C one by one, and from those figures we will get these two columns of steepness matrix. So first figure, theta B equal to 1, give the unit rotation. Now understand we are always giving the rotation in positive direction. Positive direction means, what is the positive direction of rotation? We have assumed positive direction of rotation is anti-clockwise. So we have to rotate joint B in anti-clockwise direction. Right? Now one more thing you please understand, while deriving the stiffness matrix, remove all external load acting on the beam or any structure. We are not considering any external load while deriving the stiffness matrix of particular structure. Right? So our anti-clockwise rotation or anti-clockwise moment is positive, right? So to draw the figure now, we have to give the unit rotation at point B in anti-clockwise sense. So understand, to rotate joint B in anti-clockwise sense, we have to apply a moment at joint B in anti-clockwise sense, because moment is an action corresponding to rotation. So if you want to rotate, you have to apply moment. So since we have to rotate joint B in anti-clockwise sense, we have to apply moment in anti-clockwise sense. Now since this rotation is unity, since this theta B equal to 1, The moment required to give the rotation is actually 4 EI theta by L. 4 EI theta by L is the value of moment required to rotate any joint. But since our theta is equal to 1, the moment required to rotate any joint by unit rotation, the answer is 4 EI by L is the value of moment, right? And if this moment is required to rotate that particular joint at the other joint of that member, the moment will be 2 EI by L. Okay, moment will be 2 EI by L. So please remember, when you give the unit rotation at any joint, at that joint moment is 4 EI by L, and at the other joint moment will be 2 EI by L. Now since we are rotating joint B, the moment at point B will be 4 EI by L, at the other end it will be 2 EI by L. Okay, so first figure, this is theta B equal to 1. Now understand, since we are giving rotation at point B, 4 EI by L moment is at point B. Since B is a common joint to both the members, it will be acting at both the members at point B in AB member as well as at point B in BC member. The moment is 4 EI by L, right? Now at far end means in AB member at A it will be 2 EI by L, means half of this, and at C again it will be 2 EI by L, half of this 4 EI by L. Now EI is equal to constant given to you, but I is not constant, I is varying. If you look at the given problem, if you look at this I is equal to 2I for AB member and I equal to only I for BC member. It means when you take the value of I for AB member, always take it as a 2I, right? So if you put that I equal to 2I here, 4 into E into 2I divided by L is equal to 6 meter. L is equal to 6 meter. So 4 into 2, 8 divided by 6. The answer is 1.33 EI, right? This is anti-clockwise because we are rotating joint B in anti-clockwise sense. Why we are rotating joint B in anti-clockwise sense? Because we have to rotate the joint always in positive direction. We are giving the unit displacement in positive direction. So this is 1.33 EI. At far end it will be 2 EI by L. 2 EI by L means half of 4 EI by L. So half of 1.33 is 0.67 EI. Right? This is moment required to give the unit rotation at point B. Now in second member 4 EI by L, for second member L is equal to 4, L is equal to 4 meter. So 4 upon 4 it is 1 EI, because I equal to I here. I is not varying in this case, so I is equal to only I. So 4 into E into I divided by L is equal to 4. 4 upon 4 is 1 EI, and half of that at far end it is 0.5 EI. So these are the moments required to give the unit rotation. It means these are the stiffnesses required to give the unit rotation at point B, because moment is force, and force required to give the unit displacement is nothing but stiffness. So ultimately these are the stiffness coefficients in the beam when you rotate joint B by unit rotation. Okay. Now similarly we have to draw the second figure, that is theta C equal to 1, right? Now first understand, now when you rotate joint B, how to frame the stiffness matrix now. How to frame the stiffness matrix. This I already explained. First column of stiffness matrix you will get from the first figure when you give the unit displacement, that is theta B equal to 1. First column you will get from theta B equal to 1, and second column you will get from theta C equal to 1. Right? Our unknowns are theta B and theta C. These are our unknowns, right? Two unknowns. So first coefficient K11 is corresponding to first unknown, that is theta B, and second coefficient is corresponding to second unknown, that is theta C. In both the columns, first unknown is corresponding to theta B and second unknown is corresponding to theta C. Now K11, K12, these represent the force required to give the unit rotations. So force means what? It is a action. Action means action corresponding to theta, action corresponding to rotation. So action corresponding to rotation is moment. Action corresponding to rotation is moment. So what is the value of K11? K11 will be in the first figure, that is theta B equal to 1. If first coefficient is corresponding to theta b, means first coefficient will be moment at b, because moment is an action corresponding to rotation. Then second coefficient in the first column, second unknown is theta c, corresponding action is moment at c. So values of moment at B and moment at C are the first column. Similarly, when you draw theta C equal to 1 figure, in that first unknown is theta B again, K12. So moment at B and moment at C are the second column of stiffness matrix. So please understand, since our unknowns are theta B and theta C, first unknown is theta B. So first row is corresponding to moment at B in two figures, and second row is corresponding to moment at C in second figure. First figure and second figure, right? So this is how we can collect the steepness. So this is I have written from the first figure. If you look at what we required, first element is corresponding to moment at B. First element is moment at B. What is the moment at B? In first figure AB member it is 1.33 EI, and plus in second member it is 1 EI. So addition of these two is moment at B, and that is 2.33 EI. This is 2.33 EI is taken outside the matrix, right? And then second element is what? Second element is moment at C. What is the moment at C? It is 0.5 EI. It is 0.5 EI. So this is 0.5. Like this you can write down the first column of the stiffness matrix. This is from first figure, that is theta B is equal to 1. Similarly, now we have to draw second figure, that is theta C equal to 1. So give the unit rotation at point C now. Now one more thing, please understand. In the previous figure, since we have given the unit rotation at point B and B was a common joint to both the members will be subjected to the moments, right? Because B was common. Now since in this figure we are giving the rotation at C and C is a end joint. So when you rotate joint C by unit rotation, its effect will be on joint C and joint B only, because it is BC member. But effect of rotation of C will not be on AB member. There will be no effect of rotation of C on AB member. It means moments on AB member will be 0. There is no moment on AB member, right? So this is 0. Now since we are rotating joint C, the moment 4 EI by L will be at C, and half of that at far end, that is B, 2 EI by L, right? I equal to I, we know that I equal to I for BC member, and L is equal to 4 meter. So 4 EI upon 4, 1 EI. This is the moment at C, half of that at other end, 0.5 EI. Of course 0 at point B and A in AB member. So these are the moments developed when you give the unit rotation at point C. Okay. So again, if you want to complete the stiffness matrix, now second column of stiffness matrix, right? So this is the final stiffness matrix. First column already we have written from theta B equal to 1 figure. First column we have already written from theta B equal to 1. Now second column we have to write down from second figure, that is theta C equal to 1. So first element is corresponding to theta B. We know that first element is corresponding to theta B, which is moment at B, and second element is corresponding to theta C, that is moment at C. So what is moment at B in this figure? Moment at B is 0.5 EI. So this is 0.5 first element, and second is corresponding to theta C, that is moment at C. Moment at C is 1 EI. So this is 1. So this is final stiffness matrix of the given beam. So like this you can derive the stiffness matrix of any structure by giving unit displacement one by one, right? This beam has only unknowns rotations. It may possible that your unknown will be delta, that is vertical displacement. In some cases in beam, suppose if guided support or spring support is provided, there may be delta unknown. If delta is unknown, then you have to give the unit displacement. So in that case, how the forces or actions are required, that we will discuss in the second problem. So problem number 2 is the beam is shown to you and question is to derive the stiffness matrix of the beam. So if you understand the beam now, left support is fixed, middle support is roller, and end support at C is called as slider or guided support. See here, it is guided support at point C. Guided support is also called as slider. So slider is provided at point C. What is the meaning of slider? Slider means this support allows this point 2 to move vertically up and down only. Only it allows the point C to move vertically up and down. It means vertical displacement delta is permitted, but this joint will not rotate. So there will be no rotation. Theta is equal to 0 at guided support. There is only one unknown, and that is delta, right? Similarly, at roller support, middle roller support, unknown will be theta. We know that. So theta b is unknown at roller support, delta c is unknown at guided support, and 0 kinematic unknowns at fixed support. So degree of kinematic indeterminacy of this beam is again 2, but it is theta b and delta c. Right. Now to derive the stiffness matrix of this beam, first figure is similar to previous problem. Theta b equal to 1. Give the unit positive rotation at point B. Positive means anti-clockwise. To rotate the joint B in anti-clockwise sense, we have to apply moment in anti-clockwise sense. So moment at point B is anti-clockwise in both the members, because B is common to both the members. Magnitude of moment 4 ER by L. We know that at far end it will be 2 ER by L, half of that, 4 ER by L. So it is 2 ER by L at the far end. Now in this beam problem, EI is constant as well as I is also not varying. So I is equal to only I, right? Now if you want, you can draw this deflected shape. This is deflected shape of the beam. When you rotate joint B in anti-clockwise sense, how the beam will deflect, that it represent. If you want, you can draw it. If you don't want, no problem if you don't draw it. Simply show the moment. So 4 EI by L, 4 by, what is the span of this AB member? It is 8 meter. So 4 upon 8, 0.5 EI, half of that at other end, it is 0.25 EI, that is 2 by L, 2 by 8. Similarly, in the second member, span is again 8 meter. So 4 EI by L is 0.5 again, half of that at other end is 0.25 EI. So like this you can find out the moments. Now one more important thing you have to understand. If your unknowns are only rotations, no need to find out reactions, because action corresponding to rotation is moment. So we required only moments to write down the stiffness matrix. But if your unknown is delta, that is vertical displacement, the corresponding action is vertical reaction at that point. So if your unknown is delta, you have to find out reaction at that point. In our problem, delta is at point C. We have our unknown is delta C. So the corresponding action is reaction at C. So we are interested to find out reaction at C because it is a action corresponding to delta C. Action means force. Force corresponding to delta C. So in this case, we have to find out the reactions also. But only we require reaction at C. So no need to find out reaction at A as well as reaction at B. Only find out reactions of BC member because we required reaction of C. Right. Now how to find out reactions? See, reactions can be calculated in two parts. First, reaction due to external load plus reaction due to moments. But in this beam, since we are deriving the stiffness matrix without considering any external load, there is no external load acting on the beam. So we have only moments at the ends. So it means there will be reaction due to only moments, right? So what are the moments acting on BC member? It is 0.5 EI at point B and 0.25 EI at point C. Both the moments are having anti-clockwise nature. This is anti-clockwise. Now how to find out reaction due to moment then? Reaction due to moment is sum of moment. Sum of moment, that is 0.5 EI. Anti-clockwise means positive. So sum of moment 0.5 EI plus at other end it is 0.25 EI. So sum of moment at two ends of the beam member, right? So it is MBC, here it is MBC plus MCB. Sum of moment divided by span is, let it be 8. So this is the value of reaction. Understand, sum of moment at two ends. If moment is both the moments are anti-clockwise, both the moments will be positive. If both the moments are clockwise, both the moments will be negative. If one moment is positive, one moment is negative, that is anti-clockwise and clockwise. Take the proper signs. Now in this problem, both the moments are anti-clockwise because we are rotating joint B in anti-clockwise sense. So if both the moments are anti-clockwise, both are positive. 0.5 EI plus 0.25 EI divided by span. So answer is 0.0937 EI. 0.0937 EI. This is the value of reaction. Understand? It is a value of reaction in BC member. It is a value of reaction in BC member. Understand again how to calculate reaction. It is sum of moment at two ends, sum of moment divided by span. Right? Now, what answer you are getting for this reaction? This answer is positive. This answer is positive. Right? It means the couple of reaction, if this answer is positive means what? It is anti-clockwise. Answer is positive means anti-clockwise. So reaction, since reactions are of opposite nature of acting forces, if reactions are opposite nature of acting forces, so if this answer is positive, it means anti-clockwise. So reaction must be acting in clockwise couple form. Reaction must be clockwise couple. Please understand. If sum of moment divided by span, this answer is positive means anti-clockwise, then reactions will be clockwise couple. Reactions will be acting at point B and point C, two ends of this span. So clockwise couple means left reaction must be upward and right reaction must be downward. This is clockwise couple. Please understand. Now suppose if in any problem you are getting this answer as a minus, R is equal to suppose minus. In that case, minus means clockwise. So reaction couple will be anti-clockwise. Anti-clockwise means left downward, right upward. This means it is an anti-clockwise couple, right? So we have to take anti-clockwise couple means left downward, right upward reaction, and clockwise couple means left upward and right downward. This is clockwise. So in our case, this case, it is clockwise reaction. Okay, so like this you have to find out the reaction. We are not interested in reaction at A and reaction at B, though I have mentioned, but no need to calculate it in the examination. Okay, so like this is first figure, theta B equal to 1, right? And now since our second unknown is delta C, okay, now I have just summarized the values of moment. Why these values of moment and reaction at C is written? Because we know that our unknowns are theta B and delta C. These are our unknowns. Okay, and we know that this first figure theta B equal to 1 will gives you the first column of stiffness matrix. When you write down the stiffness matrix, it will gives you first column of stiffness matrix, that is theta B equal to 1 figure. Right? So elements of stiffness matrix, first column, first element is corresponding to first unknown, that is theta B, and second element is corresponding to second unknown, that is delta C. So what is the action corresponding to theta B? It is moment at B, and action corresponding to delta C is reaction at C. And that's why this moment at B is written here. Moment at B is this 0.5 plus this 0.5, total is 1 EI, right? And reaction at C is here, it is downward, so minus magnitude is 0.09375. This is reaction at C. Okay, so these are the first column elements. Similarly, second figure is delta C equal to 1. Give the unit vertical displacement. Delta is a vertical displacement. Okay, delta is a vertical displacement. Now since we are giving the positive displacement, since we are giving always positive displacement, vertical positive means vertically upward. So this is positive sign for displacement. Upward positive, downward negative. So we have to give positive displacement means vertical displacement at point C, vertically upward. Vertically upward displacement at point C. So look at here, the vertical upward displacement is given at point C. This is upward, right? This is 1, unity, delta C equal to 1. Now again similar to previous problem, when we are giving the displacement at joint C, there will be no effect of this on AB member, right? So moments and reactions in AB member will be 0. There is no effect of delta C equal to 1 on AB member. So moments as well as reactions. So reactions are not required for AB member, but still moments as well as reactions will be equal to 0. So we have to find out moments and reactions of BC member only. Now, what is the moment required to give the unit displacement in perpendicular direction? Perpendicular means if beam is horizontal, displacement vertical. It is called as displacement in perpendicular direction. So, moment required to give the unit vertical displacement is 6 EI by L square. This is the value of moment. 6 EI by L square is the moment required to give the displacement, vertical displacement in case of beam. And in this case, moment at both the end must be same. It is 6 EI by L square at two ends. Like in case of rotation, it is 4 EI by L at near joint and 2 EI by L at far joint. But in case of vertical, when you give the vertical displacement at any point, the moment at two ends must be same, 6 EI by L square. Right? Now, L of this span is, we know that 8 meter, I equal to I only. So if you substitute this value, 6 EI divided by 8 square means 64. 6 by 64, the answer is this, 0.0937 EI. 0.0937 EI. Since it is same at two ends. Now important point is, what is the nature of this moment? What is the nature? So to decide the nature, this is what you have to give the vertical displacement. So you have to apply moment like this, clockwise moment. To give the vertical displacement, you have to apply the clockwise moment. But if you are confused to decide the nature of moment, there is a simple way. You draw one arrow in the direction of displacement. You draw one arrow in the direction of displacement and bend that arrow outside the beam. Automatically you will get the nature. It is clockwise. It is clockwise, right? So it is clockwise 0.0937. If this is clockwise at this end, again it must be clockwise at other end. So it is clockwise at both ends, 6 EI by L square. Okay, please understand how to decide the nature. Draw this arrow in the direction of displacement and bend that arrow outside the beam. You will get automatically nature. It is clockwise. Magnitude is 6 EI by L square. After substitution of 8 meter span, the answer is 0.0937 EI at both ends. And clockwise means it is minus. Now again, we are interested in reaction at C, important because reaction at C is the action corresponding to delta C. So we have to find out reaction because of moment using the same previous concept, sum of moment divided by span. So what is the moment? 0.0937. Now it is clockwise, so it is minus. So 0.0937, right? There is 9375 actually. We have written only 937. It is minus. Again this minus 0.0937, sum of two moments, both are minus, so it is minus minus become plus with the minus sign, divided by span is 8. Okay, don't forget there is EI outside. Okay, so answer will be minus 0.0234, minus 0.0234 EI, right? This is value of reaction. Okay, now answer is minus. Answer is minus. Minus represent it is clockwise. So if it is clockwise, reaction couple must be anti-clockwise. Anti-clockwise means left downward, right upward. Right? This is the reaction couple. So left downward, see here, it is left downward and right upward. Magnitude is same, 0.0234 EI. One more thing, please understand. Here it is minus answer, but we have not written minus in the here reaction, because this minus we have used to decide the clockwise and anti-clockwise nature of couple. So it is used only to decide whether the reaction couple is clockwise or anti-clockwise. Otherwise, don't use this minus to write down the magnitude of reaction. It is plus only. Magnitude is only 0.0234 EI, right? And this anti-clockwise couple, left is downward, right is upward. So this is reaction of beam, right? Now based on this, we can write down the stiffness matrix of the given beam. So this is again summarize moment at B, right? Moment at B is equal to 0 in this member because there is no effect, and here it is clockwise means minus 0.0937 EI. Similarly, second reaction at C, it is upward at C. Upward means positive 0.0234 EI, right? And based on these two figures, finally we can write down this steepness matrix. Okay, one more thing, please understand, steepness matrix is always symmetric matrix. So this minus minus term, upper triangular and lower triangular elements are always same, right? These first two elements are from theta b equal to one figure, and remaining second column from delta c equal to one figure. First element, I'll repeat again, first element represent moment at B and second element represent reaction at C, because our unknowns are theta B and delta C. In both the figures, both the cases, this is moment at B and this is reaction at C. Okay, so like this, if your delta is unknown, you can find out the steepness coefficients, right? There is one more problem I have covered in this, that is problem of frame, right? So briefly we'll cover this also. So degree of kinematic indeterminacy. Now in case of frame, these joints are called as semi-rigid joints. So there is rotation unknown at these joints. Please understand. Okay, how to determine the DKI of frame. Fixed support means it is 0 at A, 0 at D, and joint B and joint C, there is a rotation unknown always. So it is theta B unknown and theta C unknown. Now based on the whether frame is sway frame or non-sway frame, you can decide the third unknown. There will be delta present or not. So since it is an unsymmetric column of frame, as well as I is also unsymmetric, loading is also unsymmetric, this frame is a sway frame. So there will be a delta also unknown. So decay of this is equal to 3, that is theta B, theta C and delta, that is sway, right? And now one by one, if you give the unit displacement, there will be three figures, theta B equal to 1, theta C equal to 1 and delta equal to 1. This is first figure, theta B equal to 1, right? Now please understand, you have a frame like this. So B joint, when you rotate the joint B, theta B equal to 1 means you have to rotate joint B. When you rotate joint B, there will be no effect of this rotation on CD member, because B is a common joint to AB member and BC member, AB and BC. So only these two members will deflect. There will be no effect of rotation at B on CD. That's why CD member is not drawn here, right? So only two members AB and BC are shown. Now since we are rotating joint B in anti-clockwise sense, there will be anti-clockwise moment at joint B. Anti-clockwise moment. What is magnitude of that moment? 4 EI by L, right? It is anti-clockwise at point B because it is positive. So look at this. It is 4 EI by L anti-clockwise at point B. Similarly 4 EI by L anti-clockwise at B in AB member, right? And at C it will be 2 EI by L with the same anti-clockwise, 2 EI by L at C and 2 EI by L at A, right? So this is first figure. Okay, so 4 EI by L, I equal to 4I given for this AB member as well as BC member, I equal to 4I. So don't forget, you have to take I equal to 4I. So 4 into 4I means 16 EI divided by L is equal to 4. The answer is 4 EI. At far end, half of that, it is 2 EI. These are the moments on BC member. Similarly, 4 upon 4, 4 into 4 upon 10 meter for AB member, 16 upon 10, it is 1.6 EI at B and half of that 0.8 EI at A. These are the moments. Okay. Now, since our delta is also one of the unknown, delta means horizontal sway. Horizontal, we are assuming that sway will be towards right. Okay, we are assuming that sway will be towards right. Okay, so if delta is towards right, corresponding action is force, horizontal force at point B or at point C. Horizontal force at B and C point is the action corresponding to delta. Horizontal force at point B and at point C is the action corresponding to delta. Okay, so we have to find out horizontal force. Now since it is a frame, we know that horizontal forces or horizontal reactions occurs only in column because reactions of beam are vertical. So we are interested in only to find out the reactions of column. That too, we are interested only reactions at point B, not reaction at point A, right? So we have to find out reactions of AB member only. Only reactions of AB member. Please understand. Why AB only? Because AB member is vertical, force subjected to AB member is horizontal, and that's why reactions of AB member will be horizontal. Since our delta sway is horizontal, corresponding action are horizontal reaction at B plus horizontal reaction at C if both the reactions are present. If there is only one reaction, then take only that one reaction. Okay. So how to find out reaction at AB member since there is no load? So again using the same concept, sum of moment. Now what is the moment at upper end? It is 1.6 EI. So 1.6 EI, that is sum of moment plus second moment is 0.8 EI. 0.8 EI. Right, 1.6 EI upon 0.8 EI, sum of moment divided by span is 10. Span is 10. So what is the answer? 1.6 plus 0.8, it is 2.4. 2.4 EI upon 10, answer is 0.24 EI. Right, this is value of reaction. Now what is the direction of reaction? So this answer is positive. This answer is positive. Positive means what? It is anti-clockwise. So reaction couple must be clockwise. Clockwise reaction couple means top must be towards right and bottom must be towards left. So this is represent clockwise reaction. Okay, so please understand, top is towards right, bottom is towards left, means it is clockwise. Why it is clockwise? Because our answer of reaction is positive. It represents it is anti-clockwise and reaction is always of opposite sense of acting force. So it is clockwise couple. And that's why this top reaction is towards right 0.24 EI and bottom reaction is minus 0.24 EI. Okay, so like this you can calculate the reaction. Similarly, theta c equal to 1 figure. Since we are rotating joint C only, there will be no effect of joint C on AB member. So AB member is not drawn here, only BC and CD. Similar to this figure, the moment 4 EI by L at C, 4 EI by L at C in two members, 2 EI by L at D and 2 EI by L at B. So and reactions of only column, horizontal reactions of column, sum of moment divided by span, right? So like this. Now below these figures I have written the moment at B, moment at C and reaction at B. Why it is written like this? Because moment at B is the action corresponding to theta B, moment at C is the action corresponding to theta C, and reaction at B is the action corresponding to delta. Okay, so that's why we have to collect these moments only. Right, moment at B corresponding to theta B, moment at C corresponding to theta C, and horizontal reaction at B or C corresponding to delta. Now third figure is delta equal to 1. Okay, delta equal to 1. Give the horizontal sway, horizontal lateral displacement to the frame. Now since sway occurs only in column, there will be no effect of sway on the beam. I have drawn only columns here, not beam. Understand, sway, that is lateral movement of the frame. Sway occurs only in column, not in beam. So when you give the delta equal to 1, there will be no effect on beam, only columns will sway. Now since we are assuming sway is towards right, we have given displacement is towards right, that is positive direction. This is positive sway, towards right means, okay. So in both the figures, sway is given towards right, positive. Now, what is the moment required to give the sway or horizontal displacement? Like previous beam problem, if you give the vertical displacement to the beam because perpendicular to the member, beam member was horizontal, so displacement was vertical. Now here columns are vertical, so displacement is horizontal. Moment required to give this displacement is 6 EI by L square. 6 EI divided by L square. Okay, so please understand now 6. I for this left column is 4I and I for right column is only I. This is 10 meter, left column is 10 meter and right column is of 5 meter height. So 6E into 4I. So 24 EI divided by L square means 100. The answer is 0.24 EI. Moment 6 EI by L square, which is same at two ends. 6 EI by L square, which is same at two ends. Okay. Now one more thing, how to decide the nature of this moment, that already we discussed. If you are confused to decide the direction of moment, draw arrow in the direction of displacement and bend that arrow outside the beam. You will get the nature, it is anti-clockwise. It is anti-clockwise. Draw arrow in the direction of displacement and bend that arrow outside the beam. It is anti-clockwise at to both the ends. In both the column it will be anti-clockwise. Okay. So this is the moment in the column. Now how to find out reaction? Sum of moment divided by span. 0.24 EI plus 0.24 EI divided by span is 10 meter. So this reaction is 0.048 EI. Sum of moment. So 0.24 EI plus 0.24 EI, 0.48 EI divided by 10, 0.048 EI. Both the moments are anti-clockwise. So sum of these two moments will be positive. If sum of moment is positive, means reaction couple must be clockwise, opposite to the positive. Positive means anti-clockwise, so reaction couple will be clockwise. So left means top upward, top towards right and bottom towards left, right, in both the columns. So like this, what is the moment at B? 0.24 EI anti-clockwise. What is moment at C? 0.24 EI anti-clockwise. And a horizontal reaction. Now since there is a horizontal reaction in both the figures, that is joint B as well as joint C, we have to add both the horizontal reactions, right? So it is B plus C, 0.048 EI plus 0.096 EI. Answer is 0.144 EI. So like this we can summarize the stiffness elements. Okay. First column from theta B equal to 1, second column from theta C equal to 1, third column from delta equal to 1. Three columns. This is value of moment at B, this is moment at C, and this is horizontal reaction. Reaction at B in this case, here it is reaction at C, because here reaction at C is equal to 0, here reaction at B equal to 0. We have to add both the reactions of B as well as C. But in first figure there is no C reaction, in second figure there is no B reaction, but in third figure, since both the reactions are present, we have added RB plus RC, horizontal reaction. Okay, in all three columns, first element is corresponding to theta B, that is moment at C, second element is corresponding to theta C, that is moment at C, and third is reaction. So like this we have to formulate the stiffness matrix of any structure, right? So this we have discussed about the matrix, stiffness matrix formulation. In the next class I will solve one numerical example on beam to understand the complete procedure how to analyze the beam using stiffness matrix method. Okay, thank you.